Hey everyone, so we're moving on to the next part with conservation of energy. Now, this is the part where a lot of trouble ends up happening. Like I said before, we just kind of went through the equations, how to use them, and it was all standard plug and chug. But this is the one that people have the most trouble with, but it's also the most common and most important aspect conservation of energy. Now, if you recall, we already did a conservation type question, which was conservation momentum. This is going to be similar to that in the sense of the whole idea of conservation of energy is that the energy we have in the beginning equals the energy that we have at the end. The only difference is, unlike before, where we can kind of break it down by drawing pictures, and there's only really one type of momentum. Here, we have multiple types of energy that we have to deal with. Um, so again, the whole idea of conservation energy, just like with all the other conservation laws, is that we start with the amount of energy. Uh, it's going to be equal to what amount of energy we end up with. You probably heard the phrase that energy is neither created nor destroyed; it only changes forms. Because we can have potential energy from an object raised to some height, and then when we let go, it's going to lose that potential as it falls, but it's going to be moved towards other types of energies like kinetic energy, heat, anything like that. So, what I want you to do here is I want you to try to determine what I call the flow of energy, the transfer of energy. Try to figure out what type of energies are we dealing with? What type of energy are we starting with? And what is that turning into? And what's that turning into? So, pause video, work itself, and we'll go over in a second. All right. So for part A, it tells us a ball is dropped from a height. Right there, I know that the first type of energy I have is gravitational potential. And then it says that it's about to land on the ground. So it's losing that potential. But if I try to visualize what's going on, it's falling and moving towards the ground. So that means it's going to end up gaining that in the form of kinetics. So this was the scenario I portrayed before. So I know that the flow of energy is potential turns into kinetic. The next part, a book is dropped from a height, landing on the ground, and then coming to rest. So once again, we still have an object starting at a height, so it's still going to start with potential. It's going towards the ground, so it's going to be kinetic, but then it comes to rest. So it's none of the other types of energy. Remember, we have work, which is a person exerting a force on an object, potential, which is caused by height, spring potential, which is springs, kinetic, which is moving, and the fifth and final one is heat or energy lost. So the flow of energy will be this potential turns into kinetic, turns into heat. And then the third one, a book initially at rest, pushed and slides across the floor as it comes to rest. So again, it's on the table or on the floor, whatever. It's starting at rest. It doesn't have kinetic. It's pushed, which means it's going to start with some work. It's going to start sliding, so that work turns into kinetic, and then it comes to rest, which means once again I'm losing that kinetic in the form of heat. So this would be the next flow of energy. Now, the reason why this is important is that this is how we're going to develop some of the equations. Because if I ask what's the kinetic energy, in this case, well, I know it's going to be equal to whatever amount of energy I lost, and it's also equal to the amount of work being done. So this flow of energy tells me that if I start with 2 joules of work, that 2 joules turns into 2 joules of kinetic, which then turns into 2 joules of lost energy. So that's the whole point of determining the transfer, the flow of energy. So you should be able to read a scenario and identify kind of what that how the energy is going from one form to the other. If you can do this, then there will not be any energy problems that you won't be able to do. Um, yeah. Again, the whole idea of conservation is that when one of those energies changes, whether it increases or decreases, it's got to go somewhere. It's got to go into one of these other types of energies. Now, usually very common is that we're going to end up having transfers of potential to kinetic. But again, we're going to have all these other types as well. Um, so just like before, when we dealt with friction, we pretty much assumed that unless said otherwise, unless they said there was friction or they said that we had things moving on rough surfaces, we pretty much were to assume that there was no friction. The same idea holds here. For the most part, we're going to assume that no energy is being lost to heat, internal energy, to friction, or anything like that, unless there's something fishy going on. Unless they tell us that there's heat being lost or energy being lost, or they tell us that the energy we start with is different than the energy we end with, that basically tells us that we must have lost some energy to heat. Now, in order to actually do the problem, I'm going to want you to ask yourselves 5 questions, which I'm going to call the 5 questions. So the first question I want you asking yourself is there a height change? If there was a height change, you're going to say that you have potential energy on whichever side is the highest. So if you started at the height, then you start with potential. If you end at a height, you end with potential. So what you're going to end up doing is reading the question. You're going to come up with an idea of what energies we start with, what energies we end with, and by asking yourself these 5 questions, you're going to determine where the energies go. Do they go on the initial side or the final side? Or do they just not exist at all? So the first question is going to be, is there a height change? Now, these questions I'm going to ask in this specific order, mainly because first, they actually appear on the reference table somewhat in this order, but also this is the order of importance. So 1 is probably the most common question that you would ask yourself. The next question is there a speed change? Now note, I'm not asking, is there speed? Is it moving? I'm asking, is the speed changing? Does it increase its speed or is it decreasing its speed? And you're going to put kinetic energy on whichever side the object is moving. So if it starts at rest and then it ends up moving, you'd put kinetic only on the final. But if it started off moving and then either increase or decrease its speed to another speed, like it went from 2 meters per second to 5 meters per second, you would put kinetic energy on both sides. This is really the only one that actually does this. So kinetic energy goes on whichever side you're actually moving, whether you start, end, or both. The third one is there an applied force? So like, is someone physically pushing on this object? If so, work is always put on the initial side, never put on the final side. Is there friction or energy lost? Then Q goes on the final. Again, just like with the work, we can only end with heat, so we can only start with work and we can only end with heat. And the last and least common question is there a spring? And if so, then the potential energy is on whichever side the spring is. If we started off with the spring being compressed, it's initial. If we end, it's on the final. Again, these are the questions that you want to ask yourself, and I'll show a very quick example of how you would do this. So imagine this question: a block is placed on top of a 5-meter frictionless ramp, slides down, and we want to know what is the speed of the block at the bottom. So the first question we ask ourselves is there a height change? Yes, there is a height change. It's starting from the top and going down. So that means that we have potential energy on the initial side. The next question we ask ourselves is there a speed change? Well, we know that it's going to get faster, even though it doesn't explicitly say it gets faster. We know that if it places on the top, it's going to speed up as it goes down. So we're going to put kinetic energy on the final. We're not going to put it on the initial because it says it's placed, implying it's starting at rest. The next question is there a force applied? There's no mention of a person putting any force on this. Fourth question is there friction? Again, no. It says it's a frictionless ramp, so no energy is being lost. And the last one, is there a spring? No. So what this tells me is that my equation is going to look like this: PE equals KE. We started with potential energy, we ended with kinetic. Now, one of the nice things is more than half of these conservation of energy questions will end up boiling down to one energy equals another energy. So if you can read the question, just identify the two types of energies they're talking about. They talk about height and speed. Okay, we're probably setting potential equal to kinetic. Then you're golden. You're going to get a majority of the energy questions right. But there are going to be a lot of times where they're going to throw in curveballs. You have work being involved, you have kinetic energy being involved, you could have heat being involved all at the same time. So don't just resort to it's going to be energy equals energy. It could be one of these cases where three, four, or maybe all five of those questions are answered yes. So I do recommend that you always keep asking yourself the five questions as you set up the problems. All right, so we'll do a few practice questions. Oh, and then from here, I should keep going. The question was asking about the speed, and we weren't told any what the energies were. So what we would do in the next step is just substitute the equations, mgh for potential and 1/2 mv squared for kinetic, and then from here we can use the numbers to actually find the speed. So if you actually look back to that question, we had all the information we needed to figure out what the speed was at the bottom of the ramp because we have all the information for this. All right, so for these questions, I just want you to write the equations. What energy on the initial side, what energy goes on the final, and that's it. Use the five questions. So pause the video, work stuff, and we'll go over in a second. All right, so going through A, is there a height change? Yes, it's going up to the top of the ramp. Is there a speed change? No, it's moving at constant speed. So we have potential on the final side. It's going to the top. We don't have kinetic. Is there a force being applied? Yes, they actually explicitly say the work being done. So work goes on the initial. They don't say there's no friction, no energy lost, and there's no spring. So my equation will be work equals potential, and that's it. Again, I could follow up with plugging in numbers and whatever, but this is the basic step. This is the first equation. All right, part B. Ball starts at a height with some initial speed before it hits the ground. So again, is there a height change? Yes, it starts at a height, so it's going to start with potential. Is there a speed change? Yes, it does start with an initial speed, and it's going to end with even more speed as it falls down. So because there's going to be speed on both sides, we're going to have kinetic energy on both sides. Is there work being done? No. Is there friction or energy lost? No. Is there a spring? No. So my equation will look like this. PE plus KE equals KE. So we're going to have two different kinetic energies, one for the initial speed and one for the final speed. Part C, a book with some initial velocity slows to a stop. Again, going through it, there's no clear height change. There is a speed change since it starts with the velocity and then comes to a stop. So we start with kinetic energy. There's no work being done. There is friction because it's coming to a stop, and there's no spring. So because there's nothing else, we know it's kinetic energy equals heat. All right, two more. So pause the video, work itself, and we'll go over in a second. All right, so we have a book starting from rest, slides down a ramp while also heating up. So it's starting from rest at the top of a ramp. So it's going to start with potential. There is a height change. There is a speed change. It's going from rest and sliding down. So it's getting, there's going to be kinetic energy only on the final. There's no work being done. There is energy being lost to heat, and there's no spring. So we're going to end up having potential energy in the beginning equals kinetic energy plus heat at the bottom. All right. And the last one, a runner with some initial speed is pushed, causing him to run faster. There's no height change. There is a speed change, and there's speed on both sides. It starts with speed, ends with even faster speed. There is a force being acted on him, so there's going to be work, but there's no energy loss to heat, and there's no spring. So my equation will be work plus kinetic energy equals kinetic. All right. So that's pretty much the setup. Again, if you were able to read these questions and identify what type of energies we're dealing with, if you're able to use the five questions that come up to this step, That is majority of the problem. The next steps, actually plugging the equations in, is the easy part. It's the nice part. So if you can get these two aspects down, reading the question to get the flow of energy, reading the question to doing the 5 questions to figure out what energies we're dealing with and where they go on the initial and final side, then you shouldn't have any problems doing the rest of these. All right. So here's the first real question with calculation. So pause the video, work stuff. We'll go in a second. So again, we're going to go through the 5 questions. I actually have a little bit of room to go through them. Is there a height change? No. Is there a speed change? Yes. It starts at rest, but it ends with speed. So it's going to end with kinetic. Is there work being done? Yes. It actually explicitly says there's work being done. So work goes on the initial. No friction, no springs. So my equation is going to be work equals kinetic energy. Now, here's the thing. Already know what the work is. So I don't need to plug in the equation FD for work. But the question is asking what is the velocity? That's related to the kinetic energy. So I'm going to rewrite this as work equals 1/2 mv squared, because I'm going to substitute the equation we have for kinetic energy in so that I can use that to find speed. I'm not going to do anything with work because I already know what the work is. If they told me what the force and distance were, I would substitute FD in there, but for now I'm going to leave it as is. Okay, I plug my numbers in and I chug out my answer of 2 meters per second. And that's pretty much it. That's the entire problem. Again, use the 5 questions to figure out how the energies are going to be set equal to each other, which ones are being set equal to each other. Plug equations in if necessary, and then follow through to some quick algebra. That's it. Like I said, that is the bulk of the energy topic. This is the part that people have the most trouble with. Everything else, there's 2 more things that we're going to talk about. Everything else about this unit is pretty straightforward in the sense of it's a plug and chug. You find the equation for the energy, you plug the numbers in, you chug out an answer, nothing crazy. This is the only part that actually requires some extra thought. And again, if you utilize the 5 questions properly, you will end up having the problem set up the right way, and it should end up making the whole situation easier. If you have any questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.